Hey everyone, so let us solve for 2022 question paper. Right? There are again two questions, one 10 marker and one 15 marker from group theory. So this was the first one. Show that the multiplicative group which has 1 minus 1 I minus I, it is isomorphic to 0 1 2 3 modulo 4. Right? This is the first question, and there is another question, right? Prove that the homomorphic image of a group is isomorphic to some quotient group of G. Right, so this is a small tweak to the first isomorphism theorem. So because here it is given like some quotient group, we can take this as kernel basically. So let us solve this. Yeah, so the first question, G is I minus I 1 minus 1, right? And G dash is 0 1 2 3. The operation here is dot and the operation here is modulo 4, right? So let us see for the first group G, right? What is the generator here? It is I, right? And for this the generator is 1, right? So basically it is I square, I cube, I power 4. I power 4 will become 1 and I power 5 will be again I and so on. So that's why I is generator, right? Here 1 modulo 1, right? It is 2. 1 modulo 1, right? It is 3, right? 1 modulo 1, it is 0. Then again it will start from 1, right? So that's why 1 is a generator here. So let us define a function, right? Let us from G to G dash, we show that here, see, the elements both sides are same, right? If we show that the function is 1 1, then it will be automatically onto, right? Because the number of elements are same here and here. So 1 1 means it will be definitely onto. And next thing what we have to show is F is a homomorphism, right? If F is homomorphism 1 1 and onto, then it is isomorphism, right? So let us see how we will define the function, right? Everything in the domain can be written as I power m, right? I define this as m modulo 4 here, right? So see, like, so I power 1 will be 1 modulo 4. It will be for 1. I square will be for 2. I cube will be for 3. And I power 4 will be for 4 modulo 4 is 0. This will, so this is my mapping. So see here, I is mapped to 1. I square is mapped to 2. I cube is 3. I power 4 is 0. I square means minus 1. I cube is minus I power 4 is 1. So if you see, every element is mapping to different elements, so it is 1 1, right? And since both the number of elements in the both sides are same, right? So it is onto also. So only thing we have to show is it is a homomorphism, right? Let us take into I power n, right? We have to show that f of a dot b, basically to prove that it is a homomorphism, f of a star f of b, right? Star is the operation on second group, dot is the operation on first group, right? So every element can be written as I power m into I power n, right? See, this is f of I power m plus n, right? This is m plus n modulo 4, right? So this is m modulo 4 plus n modulo 4 modulo 4, right? So yeah, so what we can write here, m modulo 4 and n modulo 4, right? So here I am neglecting this modulo 4, right? Because see, m modulo 4, the range will be, yeah, m modulo 4 you can write, right? So this will be m modulo 4 is f of I power m, right? Plus this one is f of I power m. Therefore f is homomorphism. Therefore it is isomorphic, right? Because f is both 1 and onto also. We have proved that earlier. Coming to the second question, right? F from G to G dash, right? So what he said was homomorphic domain, right? Homomorphic domain will be f of G and this will be G dash, right? What he was saying was there exists a quotient function G by some say K, where K should be a normal subgroup, right? Is isomorphic to f of G, not G dash, right? This one we need to prove. See that the catch here is we see the isomorphic theorem, right? So what does it say? If there exists a G to G dash and it is homomorphic, it is homomorphic and onto, right? Then G by K to G dash there will be a isomorphism, right? This is the first isomorphic theorem, right? So here the catch is we have to consider G to f of G instead of G dash, right? This is G dash and here f of G. Now since we are considering f of G, this will be definitely onto function, right? Because we are taking a subset, right? And also f of G is a subgroup. So now from here the proof will be same as first isomorphic first theorem proof, where you will solve G by K equal to G dash, right? How will we define a function here? F of G of Ka is equal to f of A. This is how we define the function, right? Yeah, that's it. So basically you have to do the isomorphic theorem proof here. Let us do anyway. So G of Ka, right? Let us show first this is a 1-1 function. G of Ka is equal to G of Kb, right? This implies f of A is equal to f of B, right? This implies f of AB inverse is equal to E star, right? This implies AB belongs to K. This implies Ka is equal to Kb. Therefore it is 1-1. Because to show 1-1, right, we assume G of x1 is equal to x2 and we have to show that x1 is equal to x2. So this is 1-1 and we have to show that this is onto, right? So here we have f of G, right? For every f of G we have an element in G, and for every element in G we have an quotient group, right? So that's why for every x belongs to f of G, for y belongs to f of G, we have x belongs to G, and for x belongs to G we have kx here. Therefore this is onto, and what is left, we have to show that this function is homomorphism also, right? Because homomorphism plus 1-1 plus onto will be isomorphic, right? So G of K into Kb, if we show that it will be g of ka into g of kb, then we are done, right? So g of ka is f of, sorry, we have to show this one, right? So now consider this one, right? ka into kb will be kab, right? G of kab. So this will be kab will be g of ab, sorry, f of ab. This how we define. This will be f of a into f of b, since f is already a homomorphism, right? But f of a is g of ka and f of b is g of kb. Therefore g is homomorphic. So we are done. That's it.